So the last part in chapter 1 is learning about functional groups and writing organic structures. This is a very fundamental thing about organic, is to make sure that you learn the appropriate way of writing organic structures, and you learn to recognize the functional groups. Okay, so you will need this for organic 1 and 2, and then if you go on to biochemistry, you will need all of them. So let's look at the classes of compounds first. Classification of compounds in organic chemistry is based on functional group, and a functional group is where reactions usually will take place. If there is no functional group, then generally the compound is very unreactive. Okay, so for example, alkanes don't really have a functional group, and so they are the least reactive. However, we do classify alkanes as a functional group, not because of their reactivity, but just because it puts them in a category. Okay, and so they are just a class of compounds. There are three broad classes or categories of compounds. One, which are just plain hydrocarbons, which means containing hydrogen and carbon. Then we have compounds containing oxygen, and then compounds containing nitrogen. It doesn't really mean that you don't have compounds containing oxygen and nitrogen, or vice versa, or hydrocarbons or halogens, but these are just some of the easier classifications to do. So we classify them like this, and we learn them like this, and then you apply it to different compounds. Organic compounds are also classified as aliphatic and aromatic. Aliphatic is straight chain compounds, and aromatic are like benzene rings. Okay, and benzene ring is probably one of the most identified molecule of organic chemistry. It's very easy to recognize. So anyhow, those two are also classifications. Typically, you will not see it that much. You will see the other classifications a lot more. And finally, functional groups are also classified as families. So as I mentioned to you, alkanes, we kind of just say it's a family because they don't really react very much. So not a functional group, but just a family. And then there is a homologous series. In the homologous series, what you have is a series of compounds which are increasing by one carbon. Okay, that's it. You start wondering, how is organic chemistry so big? And it is so big because each of these classes of compounds have so many compounds in them. Okay, and so that is defined as a homologous series. Okay, so as we go on further and further, you increase the number of carbons in that particular family. The nomenclature in organic chemistry is very systematic. There's general names also, which we will learn about, but otherwise, if you follow the most systematic nomenclature, then you can tell very easily what kind of a compound you're talking about, which means what kind of functional group you're talking about, and how many carbon atoms. Those are the two most important things in any kind of a compound. So if you follow the systematic way, then it's very, very easy. So this is how it goes with the number of carbons. It goes up to 20. I need you to know 1 through 10. So for 1 carbon, it's meth. Then for 2 carbons, eth. 3 carbons, prop. And then bute, pent, hex, hept, oct, non, dec. This goes all the way to 10. So this just tells you the number of carbons in there. So the family name, okay, is how you would end any compound. So for example, an alkane functional group would end in ane, an alcohol functional group will end in -ol, an aldehyde will end in -al, and then -one is for ketone. Okay, and so for 1 carbon alkane, that would be methane. For a 4 carbon compound containing an alcohol, it would be butanol. And for 2 carbon containing aldehyde, it would be ethanol. It's a very systematic name, so you really cannot get confused with what kind of functional group we are talking about or how many carbons we are talking about. Again, just 1 through 10. Here are the different functional groups, and I want to take just a little bit time on telling you the key features of it. The rest of it, you have to memorize it yourself. There is no other way for it. For alkanes, it's all single bonds, okay? There's another chart I've uploaded for you on our class website, which has a little bit more details on it. This one has the structure, so I like this one also, okay? So make sure you print this one as well. Here we have alkane functional group, which is just CC bonds, single bonds, okay, between carbon and carbon. And here are some examples. Okay, just one example, sorry, ethane. For alkene, you have a double bond in there, and here are some examples for it. For alkynes, there will be a triple bond, and here are some examples. Again, look at the names of all of this, okay? It kind of gives you a little idea how the nomenclature also works. Ethane, two carbons, eth, alkane, ane. Ethene for two carbons, alkene, okay? And so on. For aromatic, aromatic is a benzene-like ring. Now, benzene are not the only compounds that are aromatic, but this is the most recognized one, so we're going to talk about it now. But we will address this a lot more in organic too when we actually study our aromatic compounds in details. But for now, this is the only aromatic compound you know about. Haloalkanes is also a family in which case one hydrogen from an alkane is replaced by one halogen. A halogen can be any one, fluorine, chlorine, bromine, whichever one. So that would be a haloalkane. An alcohol is when a hydrogen is replaced by an OH group. Um, do not confuse this with hydroxide. Okay, this is not hydroxide, this is an OH group. So that would be an alcohol. In case of an ether, that second hydrogen is also gone. Okay, this one hydrogen from alcohol is also gone, replaced by carbon. So an ether will look like a carbon, oxygen, carbon. That's how you should find an ether in any kind of a compound. So these are some of the first functional groups, okay, and we will do alkane, alkene, alkynes, and haloalkanes in organic 1. The rest we do in organic 2. Here's the next part, and let me talk about aldehyde first. We'll talk about amine in a second. Aldehyde, ketone, carboxylic acid, ester, and amide. If you look at all of these, they have a C double bond O. In the ether and alcohol, it was a C single bond oxygen. Here it is a C double bond O. These compounds are also called carbonyls. We can talk more about it later on, but for now, you just need to know that the C double bond O is a very different kind of a bond. And so aldehyde, ketone, carboxylic esters, carboxylic acids and esters, you will find the C double bond O in there. In aldehyde, this bond right here, C double bond O, is connected to a hydrogen. So this is what it looks like. In short form, it also looks like CHO. In case of a ketone, the ketone functional group, the C double bond O, is surrounded by two carbons. Okay, so which means it's in the middle. Okay, somewhere. Usually these kind of functional groups are called internal functional groups. Carboxylic acid is where the C double bond O is connected to an OH group. Okay, and carboxylic acids are the acids of organic chemistry, and you've seen these before in Gen Chem 2. So this is carboxylic acid. Carboxylic ester is when you take the acid and take the acidic proton out and add a carbon there somewhere, and or any number of carbons. It could be 1, 2, 3, whatever it is, but there's a carbon here. So here's the ester, okay, that you're looking at. So no hydrogen. Esters can be in the middle also because they are surrounded by carbons. The amide linkage has the carbonyl also, C double bond O, but then that C double bond O is connected to a nitrogen, okay, and so that's what makes an amide, okay, a C double bond O, N. That's what it should look like. Let me come back here to amine, and amines are where carbon is connected to a nitrogen, okay, that's what amines are. All of this stuff we will do in organic too. Nitriles is probably one of the least common functional group that you will encounter, okay, because C triple bond N, these compounds are not very common, and so we will probably talk about it more in organic 2 than organic 1. Let's look at chemical formulas now. This is an important part of organic as well, writing the right structure, recognizing the structure, and so on. So the full structure formula is something like this, where you can clearly see what the carbons are and how they're connected to the hydrogens. This compound is acetic acid, which you're familiar with from Gen Chem 2. So you can see how the bonding is occurring between carbon and hydrogen, carbon and oxygen, and so on. The line formula is where you don't see any carbons. Okay, so we have what we call invisible carbons. So we kind of know they're there, but we just don't write them. And the same thing happens with the hydrogens. We don't write the hydrogens out, but we know they are there. And that's the purpose of the line formula, is to simplify and make the structure neat. Okay, so you don't look at anything that you don't need to look. Oxygen here, these are called heteroatoms. So anything other than carbon and hydrogen is called a heteroatom because it's not carbon or hydrogen. So nitrogen, sulfur, oxygen, all of these are heteroatoms. So, and the other part about this is that this is a functional group. When you have a functional group, you really have to draw it out, okay, including the hydrogen in that functional group. So this line structure then does not show the CH3 over here, which it is there, but it doesn't really quite show it. So it's understood that this point over here is carbon, this point over here is carbon, and then of course the OH groups. That's the line formula. The condensed structure formula is when you write everything out in a line. And in some cases you can do the condensed structure, in some cases you cannot. So it depends. If it's a straight chain, it's not really a problem, but sometimes for cyclic structures, it's a little bit harder. So here, what you do is you go atom by atom. So C, which has 3 hydrogens connected to it, and then another C, carbon, which has 2 oxygens connected to it, and then the hydrogen. Okay, so you just write everything as it is connected. The molecular formula is, which just tells you how many carbons, hydrogens, and oxygen this compound has. So it could be for any compound, which just tells you how many total atoms are there. It doesn't tell you anything about the structure of the compound or what functional group there might be. And then the empirical formula is the lowest ratio. So in this case, for acetic acid, we can divide this molecular formula by 2. And so the empirical formula for this one will be CH2O. So these are the different ways of writing chemical formulas. For most organic chemistry part, you will see the first 3. Okay, you will see the full structure, you will see the line structure, and the condensed structure. Regarding the molecular formula, you will see this a lot also, but only in certain chapters, okay, not all throughout. So these 3, the first 3 are more common. Here are some more examples of writing out the structures. So go through this one of how these structures look. It is always a good idea to keep the angles going, okay, because each carbon over here is sp3 hybridized. So try and keep the angles as much as possible. It's a good habit, okay, when you try to draw the structures out, so they look kind of real, okay, in that matter. What this structure tells you is how they can be drawn, but all these structures are exactly the same, okay. So look through this a little bit and you will see they're exactly the same, but they're drawn slightly different, okay, which means that it doesn't really matter. In organic chemistry, you will see that connectivity is the most important thing, not how you draw it, but how you connect things. The condensed structure is usually very straightforward. Um, if you take this compound over here, okay, and then try to write the condensed structure, this is how you would write it, okay. The bond coming out of the carbon, this is not the best way to do it, okay. So don't do this one. This is a good way of doing it, all right. And then this way, all of these are appropriate structures. Now you can see the difference between this one here is that the OH is in brackets and here it is not in brackets, and that's an optional thing for you. You can either write that in brackets or not, okay. It's not required. Of course, if you have 2 OHs, then it might be better that you put it in brackets and write 2, okay. But otherwise, you can write either structures. So for example, in this structure, the last one over here, this is CH3, 2 CHOH, and the CH3s that are 2 are actually coming from here and here, all right. So these 2 you can combine because they are the same things, all right. You can't combine them if they're too far apart, but they're connected to this middle carbon, so you can combine these 2 and then write the structure, this condensed formula out. Here are some line formulas. One of the most important thing in drawing a line formula is again maintaining the angle, okay. It's really important that you maintain the angle. The structure looks nice and neat. It looks good, so make sure of that. regarding this chlorine over here for this structure, this chlorine should be drawn down here and not up there because that looks awkward. So try and make your structure look good, okay? The heteroatoms should be shown, okay? Again, as I said, so make sure that you draw the heteroatoms out. Here again we have a CH3, so this line here extending, this end point, that indicates the CH3, CH3. This is CH2, CH3. That's how we have from condensed, from the structure formula to the line formula. Cyclic compounds are just lines. So for example, if you have 3 carbons joined in a ring, then it'll just a triangle. If you have 4, it's just a square, so on and so forth. If you have multiple bonds, then you draw the multiple bonds exactly where they're supposed to be. Okay, so 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. Between the second and third carbon, there's a double bond. Between the second and third, there is a double bond. Okay, always good idea to count your carbons if you're not quite sure. Here is an example of just functional groups. Okay, drawing the line structures and all that, you really have to practice that separately. But here's an example of a functional group. Okay, so you can have one big compound which can have many functional groups in it. Okay, so this one, for example, has an ester right here, C double bond O, then connected to the oxygen, which is connected to a carbon. That makes it an ester. Here is an alcohol, OH. Here is a ketone, carbon, carbon with an oxygen, and then carbon. Okay, so that makes it a ketone. Here is a ketone, again, carbon, double bonded oxygen connected to a carbon and another carbon. Here's an alkene and here's another ketone. Okay, so here's an example for you. Finally, the keywords and the concepts for this chapter is you need to know the fundamentals, which is the meth, eth, prop kind of fundamentals for naming organic compounds. Functional groups, all of them. You must know them. Okay, all of them. And then writing the organic formulas, different ways of expressing organic structures. So those are the important things from this part, okay, of the chapter.